Black holes consume everything. Light can't escape. Matter vanishes forever. The ultimate cosmic trap. Gravity so strong that once you cross that boundary, the event horizon, you're gone. Done. Everyone knows this. It's in every textbook, every documentary, every casual explanation of what black holes are. But do they last forever? What happens to all that trapped information, every particle, every photon that fell in over billions of years? Can something that only takes in ever give anything back? If nothing escapes, how could a black hole possibly shrink? The answer everyone gives is simple. Nothing escapes a black hole. It's a fundamental law of general relativity. Except it's wrong. Black holes evaporate. They glow. They die. The reason has nothing to do with what falls in. It's about what happens at the edge, where quantum mechanics meets gravity's most violent arena. The classical picture of black holes bothered me in the early 1970s. According to general relativity, a black hole is a one-way street, a cosmic drain. It gets bigger by eating stars and gas and light, but it never gets smaller. Ever. And that creates a problem, a terrible problem for thermodynamics. See, thermodynamics says that entropy, disorder, roughly speaking, can never decrease in a closed system. It always increases. But if you throw something with entropy into a black hole, that entropy seems to disappear from the universe. Just gone. Vanished beyond the event horizon. The universe appears to have less disorder than it did before. That can't be right. Thermodynamics always wins. Always. It's perhaps the most ironclad principle in all of physics. So something was wrong with this picture. Jacob Bekenstein, a graduate student at Princeton, suggested something radical in 1972. He proposed that black holes themselves have entropy, that the event horizon, the surface area of the point of no return, is a measure of the black hole's entropy. More area, more entropy. If that's true, then thermodynamics is saved. The entropy didn't disappear when you threw something in. It got added to the black hole's entropy. Brilliant. But there's a catch. In thermodynamics, if something has entropy, it must have temperature. And if it has temperature, it must radiate. Everything with temperature radiates. A hot coal glows. Your body radiates infrared. Even the cosmic microwave background is thermal radiation from the universe itself at 2.7 degrees above absolute zero. So if black holes have temperature, they must radiate too. I thought Bekenstein was wrong. I tried to prove it. I worked through the quantum field theory near the event horizon, expecting to show that black holes don't radiate, that they can't have temperature. The mathematics forced me to an uncomfortable conclusion. The calculation showed something impossible. Black holes glow. They emit thermal radiation, just like a hot coal. The temperature is inversely proportional to the mass. Bigger black holes are colder. Smaller ones are hotter. I was so surprised that I made a mistake in my calculation at first. I thought I'd found an error in the mathematics. But no. The result held up. Now the usual explanation you'll hear goes like this. Space isn't empty. Even what we call vacuum is seething with activity. Virtual particle pairs constantly popping into existence and then annihilating each other almost instantly. An electron and positron appear, exist for a fleeting moment, then recombine and disappear. This happens everywhere, all the time. Near a black hole's event horizon, one particle of the pair can fall into the black hole, while the other escapes. The escaping particle becomes real radiation. The one that fell in has negative energy, which reduces the black hole's mass. That's the usual story. It's not quite right, but it captures something true about the process. The more precise explanation is that the quantum field gets twisted by the curved space-time near the horizon. What looks like a vacuum state to someone far away looks like a state filled with particles to someone near the horizon. The geometry itself creates particles from nothing. It's not really about pairs splitting apart. It's about how different observers see the quantum field differently in curved spacetime. But either way, you end up with the same result: radiation escaping from the black hole. Which raises the question, where's the energy coming from? The escaping radiation carries energy. Energy must come from somewhere. You can't create it from nothing. The only source is the black hole itself. As radiation escapes, the black hole's mass decreases. The black hole is evaporating. Well, not evaporating like water. More like slowly converting its mass into radiation, bit by bit, through quantum effects at the horizon. For a stellar mass black hole, say 10 times the mass of the Sun, the temperature is absurdly cold. Billionths of a degree above absolute zero. Far colder than the cosmic microwave background, so these black holes actually absorb more radiation from the universe than they emit. They're growing, not shrinking. But smaller black holes are hotter. The temperature goes inversely with mass, so a black hole with half the mass has twice the temperature. And here's where it gets strange. As the black hole loses mass, its temperature increases. Higher temperature means it radiates faster. Radiating faster means it loses mass faster still. The process accelerates. It runs away. A black hole doesn't evaporate at a steady rate. It gets hotter and hotter as it shrinks, radiating more and more energy, losing mass faster and faster. The final moments are an explosion of radiation. Curiously, a black hole with the mass of a mountain would explode with the energy of 1,000,000 hydrogen bombs. Small black holes evaporate quickly. A microscopic black hole, if such a thing exists, could evaporate in a fraction of a second. But stellar mass black holes? They take an absurdly long time. A black hole with the Sun's mass would take about 10 to the 67th power years to evaporate completely. That's 10 with 67 zeros after it. For comparison, the universe is currently only about 14 billion years old. That's 10 to the 10th power years. Supermassive black holes at the centers of galaxies, millions or billions of solar masses, take even longer. 10 to the 100th power years. A Google years? We've looked for the explosions from small primordial black holes that might have formed in the early universe from density fluctuations. Haven't found them. Which tells us that primordial black holes, if they exist at all, aren't common in that mass range. So nothing lasts forever, not even the ultimate trap. But this creates a terrible problem. Quantum mechanics has a fundamental principle. Information is never destroyed. The quantum state of a system evolves in time, but it's always reversible in principle. You could run the equations backward and recover what you started with. That's unitarity, the conservation of quantum information. But black hole evaporation appears to violate this. The radiation coming out is thermal, random. It has no structure, no correlations that would encode what fell into the black hole. A black hole could swallow an encyclopedia or an equivalent mass of random hydrogen atoms, and the outgoing radiation would be statistically identical. The information about what fell in seems lost forever. That violates quantum mechanics. For years, decades actually, I argued that information is lost when black holes evaporate, that quantum mechanics had to be modified, that this was a genuine exception to unitarity. I was wrong. The current understanding, supported by string theory calculations and other approaches, is that the information is encoded in the radiation. Somehow. The Hawking radiation isn't perfectly thermal after all. There are subtle correlations between the emitted particles that carry the information back out. The radiation is very nearly thermal, but not exactly. Those tiny deviations contain all the information about what fell in. We don't fully understand how this works yet. The mechanism is still being worked out. But the mathematics suggests the information does escape. That's still being debated and refined, but most physicists now believe information is preserved. The deeper issue is why this happens at all. Hawking radiation is a pure quantum gravity effect. You need both general relativity, curved spacetime, event horizons, black holes, and quantum mechanics, uncertainty principle, quantum fields, virtual particles, to predict it. Neither theory alone tells you black holes evaporate. Classical general relativity says nothing escapes. The event horizon is an absolute boundary. Quantum mechanics by itself doesn't even have black holes. It was developed for atoms and particles, not gravity. But when you combine them, when you do quantum field theory in the curved space-time around a black hole, evaporation falls out of the mathematics. This is one of the very few places where we can actually calculate something definite about quantum gravity. Most quantum gravity effects happen at the Planck scale, distances of 10 to the minus 35 meters, energies far beyond anything we can produce in particle accelerators, completely inaccessible to experiment. But near a black hole event horizon, quantum effects get amplified by the extreme geometry. The curvature of space-time is so severe that quantum fields behave in measurable ways. Well, measurable in principle, the radiation is far too weak to detect from any real black hole. But we can calculate what it should be, and the calculation is solid. In 1974, when I announced this result, people thought I'd made an error. Dennis Sciama, my PhD supervisor, was skeptical. Other physicists checked the calculation, found different mistakes, corrected them. It took months before the result was generally accepted. But it held up. Black holes radiate, which means something profound about the future. The universe is currently 13.8 billion years old. Stars are still forming, galaxies are still colliding, black holes are still growing. But this won't last. In a few trillion years, star formation will cease. The universe will have used up its supply of hydrogen gas. The last red dwarf stars will burn out after 10 trillion years or so. By comparison, stars will all die in mere trillions of years. After that, the universe will be dark, cold. Just stellar remnants, white dwarfs, neutron stars, black holes, and planets drifting through an ever-expanding void. And eventually, even the white dwarfs and neutron stars might decay or get swallowed by black holes. The last remaining objects in the universe will be black holes, and they too will evaporate. Stellar mass black holes will take 10 to the 67th power years. Supermassive black holes will take 10 to the 100th power years. But they will evaporate, every one of them. And when they're gone, all that's left is a cold, diffuse sea of radiation, photons and neutrinos spreading through an ever larger space, getting colder and colder as the universe expands. Heat death, complete thermodynamic equilibrium, maximum entropy. Everything that ever existed, stars, planets, people, civilizations, all the information processed by all the minds that ever existed, eventually becomes dispersed thermal radiation. The universe doesn't end with a bang or whimper. It fades. Actually, there might be other factors. Dark energy could behave differently in the far future. Vacuum decay could destroy everything suddenly. Exotic new physics could emerge. But if nothing exotic happens, if the laws we know continue to apply, this is the fate. Return to the beginning question. What does black hole evaporation reveal? Black holes aren't permanent prisons. They're temporary storage. Everything that falls in does eventually come back. Out, scrambled beyond recognition, encoded in thermal radiation, but it comes back out. The event horizon isn't an absolute boundary. It's permeable to quantum effects. Information can escape. Gravity and quantum mechanics must be unified into a single framework. We don't have that complete theory yet. String theory is one attempt. Loop quantum gravity is another. There are others. They all predict Hawking radiation, which is encouraging, different approaches converging on the same result. But we don't have experimental evidence. Real Hawking radiation from real black holes is far too weak to detect. A solar mass black hole radiates with a temperature of about 60 nanokelvin, 60 billionths of a degree, above absolute zero. The power output is about 10 to the minus 28 watts, utterly undetectable with any technology we can imagine. But the mathematics is consistent across multiple approaches. The calculation has been done in different ways by different people, and they all agree. So we started with nothing escapes a black hole. That's wrong, at least at the quantum level. Black holes evaporate. They have temperature. They radiate. They die. The universe is not permanent. Even the most enduring objects eventually fade away. And the information paradox, where exactly the information is encoded in the radiation, how it escapes, that's still not fully solved. Next question, what happened to the information that fell in during those first billions of years of evaporation? Where exactly is it encoded in the radiation being emitted now? We have arguments. Calculations from string theory suggest it's there. Holographic principles suggest the horizon encodes it. But we don't have proof. We don't have the complete mechanism. That's the frontier. I spent decades thinking about it. Changed my mind more than once about whether information is truly lost. The answer, when we find it, will tell us something fundamental about reality itself, about how quantum mechanics and gravity fit together. But I've got to stop somewhere. Perhaps someone reading this will solve it.